Good morning, everyone. So today we will start our discussion on basic blocks and control flow graphs. So as you have seen before, and we have spent quite a bit of time on how to convert a source program, into AST. So we spent quite a bit of time trying to understand this translation process and what are the right data structures to represent an abstract syntax tree. What are the tree traversal mechanisms that we can use to make multiple passes on the constructed abstract syntax tree. Among the passes on the AST, one important pass is a pass which lowers the tree structured AST to a linear IR, linear intermediate representation. So the IR that you are seeing on the right hand side, it's what is called as a tree address tuples, linear IR. And specifically, we are looking at tree address tuples. So what is a tree address tuple? Every instruction in tree address tuple, it is of this form, x is equal to y offset. So there will be two source operands or maximum of two source operands and one destination operand will be present. So here you are seeing the code to initialize a matrix, a two-dimensional matrix. There is a first 2D loop which initializes all the entries of the matrix to 0. And then there is a second loop, which is a one-dimensional loop, which sets the elements along the diagonal to 1. So essentially, the code that you are seeing here, it constructs an identity matrix. So that is the code here. The rest of the elements are all zeros. And you can see the code, if you see the code here, there is a code, the code corresponding to the inner for loop, the tuples here. So starting from instruction 3 to instruction 9, they correspond to the inner for loop, where we iterate over the iteration over the element j. So we use j to perform iterations on the body of the loop. And then you can see the outer loop is from the outer loop, that is the loop corresponding to the variable I. It starts from statement 2 and it ends at statement 11. So the outer loop goes from 2 to 11. In fact, even statement 1 also corresponds to outer loop. It sets up things properly so that we can enter the loop. And then you can see this inner loop 9 to 3 is the, 3 to 9 rather. The instructions 3 to 9. They correspond to the inner loop. And of course, statement 2 here, it sets up, it's a precursor. It sets up things nicely for the inner loop to execute, where we set, before we enter the loop, we want to see that the value, the value of the variable j is set to 1. And then similarly, instructions 12 to 17, where instruction 12 is what do I call, it sets up the things for the loop to execute properly. Instructions 12 to 17, so they correspond to the second for loop. So your source program is constructed to AST, and your AST is converted to a sequence of 3 address tuples, and we can see that there is a mapping from the source code to the generated sequence of 3 address tuples. Few things I would like you to observe here is, yeah, maybe I will point those things out in some other example. So given this sequence of 3 address tuples, we would like to identify what are called as basic blocks. What is a basic block? A basic block is a maximal sequence of consecutive 3 address instructions such that the following conditions are uh, satisfied. The first condition is control can enter only at the beginning of the basic block, and control can leave only after the last instruction of the basic block. So actually there are two conditions. The first condition is a maximality condition. The second condition is control should enter only at the beginning of the basic block. And the second condition is, this is the second condition. This is that control should enter only at the beginning of the basic block. And the third condition is this, that the control should exit only from the end of the basic block. And the first condition is the maximality criterion. That is, we should not be able to stretch this basic block upwards or downwards. What does it mean? We will see in a moment through an example. This maximality condition, it is best understood through an example. And the first instruction of a basic block we call as its leader. So remember 3 conditions. One is the basic block should be maximal. Second condition is we should control can enter only at the beginning of the basic block. Third condition is control can leave only at the end of the basic block after the last instruction. So let's try to understand. So we have this example. The first question is the instruction sequence starting with 1 and 1. So let's call it as, so this means the basic block consists of only one instruction. This is, so 1 means this. So is this a basic block? So the first condition, the condition that, let's look at the second condition. The second condition is control should enter at the beginning of the basic block. So if you see, the only way control can enter this basic block is only when this function is being called. And then you can also see that the control can leave this basic block only after instruction 1 is executed. So the two conditions are satisfied. Control entering the beginning of the basic block and control leaving only at the end of the basic block, they are satisfied. But we want to check the maximality condition. So if you see this basic block, we can extend this basic block only in the downward direction. We cannot extend it in the upward direction. So let's see, if we extend it in the downward direction, then what happens is the basic block that we will have will be 1, 2. So that is what we are considering here. This is a second example, 1, 2. So if you see the second example, in the second example, it's not a basic block because you can notice that, that in statement 11, there is a statement which says that if this condition is satisfied, jump to statement 2. What it means is control can enter the middle of the basic block. So because of this, this is not a valid basic block. 1, 2 is not a valid basic block because it is possible to jump to the middle of the basic block via the statement 11. So this tells us two things. Number one is that 1, 2, this is not a basic block. And it also tells us that 1, 1 is a basic block because you cannot extend 1, 1 further. So 1, 1 is a basic block. This is a basic block. And this is not. not a basic block. So similarly, if you look at uh, the basic block, the sequence of statements 1, 3, again, it's easy to conclude it is not a basic block because control can enter into here. So if you look at, even if you consider the sequence of 3 statements, so you can see that there are 2 entry points to this basic block. One entry point is statement 3 via this go to statement, and another entry point is 2. So because of these 2 go to statements, uh, the sequence of statements 1, 2, 3, they are not basic blocks. So again, not a basic block. So similarly, if you look sequence of statements 2, 5. So again, sequence of statements 2, 5, they are not valid. It's not a valid basic block because not because of this statement 11, because statement 11 says that you can enter the basic block. You can enter, the control can enter here, but that is already because you are entering it at the beginning of the basic block. But the problematic statement is statement 9, which says that you can go to statement 3 directly. That is, you are jumping into the middle of this basic block 2, 5 at the point at the instruction 3. So this is also not a valid basic block. How about I3 to I5? So this is an interesting example. So if you look at I3 to I5, so this is I3 to I5. You can see because of statement 9, control can enter. We are considering this example now. Control can enter at instruction 3, but that is already because the control is entering at the beginning of the basic block. And so there is no other instruction which permits control flow to enter at instruction 4 or instruction 5. So the entry condition is not violated. Similarly, the exit condition is also not violated because control is only leaving at statement 5. Control is leaving only at statement 5. So the entry and exit conditions are satisfied. But the problem is the maximality condition is not satisfied. What is the maximality condition? That if we include one more instruction in the basic block, in that sequence, then the entry and exit conditions are still satisfied, then the maximality condition is not satisfied. So if you extend this, if you add instruction 6 to this, okay, if you add instruction 6 to this, then what happens is it is still a valid basic block. Now it's not a valid basic block. The entry and exit conditions are still satisfied. So is the case if you add instruction I7 also, the entry and exit conditions are satisfied. If you add I8 also, the entry and exit conditions are satisfied. If you add I9 also, the entry and exit conditions are satisfied. But if you add I10, then it becomes problem, because once we add I10, why is it a problem? Because from I9, you can jump from the middle of the basic block. You don't need to go to I10 compulsory. So the exit condition will not be satisfied. So because of that, so I3 to, if you consider I3 to I9, which is the next example, this is a valid basic block. And I3 to I5, this is not a valid basic block, not a valid basic block. Why? The maximality condition is not satisfied. Maximality condition violated. So similarly, if you take this example I3 to I10, so this is not valid. So why is the condition? Why? What's the problem? We are exit from the middle of the bill. Exit from the middle. Middle means not necessarily exactly middle, somewhere in the middle of the basic block, uh, not at the exit point. Uh, the control is leaving. So here you can see. So this is let's say this is I3, I9, I10. So after I9, control can leave the basic block. We don't need to come out of the instruction I10. So because of that, I3 to I10, it's not a valid basic. So we take this sequence of 3 address tuples and construct and partition the sequence of 3 address tuples into basic blocks. So how do we do the partition? So let's see. So how do we do the partition? So here we start with instruction 1. So instruction 1, and if you include instruction 2, then it's not a uh, valid basic block because of 11. Because of 11. So 1 is the first basic block. And then you start with 2. You start with 2, you draw a line here, you draw a line here, you start with 2 and you want to extend it further. So you start with 2 and you want to include 3. If you want to include 3 in the basic block, there is a problem because of statement 9, which has a go to statement to 3. So the next basic block is 2, 2. So you say this is the next basic block. And then you start with 3 and then you include 4. You include 4, no problem. You include 5, no problem. You include 6, you include 7, you include 8, you include 9, and you cannot include 10, so you have to stop at 9. So this is this whole 3 to 9, it is one valid basic block. And then you have 10, and then you can also include 11. So you start with 10. You can also include 11 if I'm right. But we cannot include 12 because statement 11 has a go to. That means control can leave in the middle of the basic block. So we have to stop at 11. So this is the next. And then you start with 12. And you cannot include 13 because if you see statement 17 has a go to 13, so we have to break it here. And then you start at statement 13. We can include 14, 15, 16, 17. So we have this. So this sequence of 3 address tuples in your program, you partition them into basic blocks using this approach. And once you construct these or identify these basic blocks, you give a new representation for your program. So we will see that new representation is what is called as control flow graph representation for the program. Yeah, so this is what we did. So here we have got the control flow representation of the program. And you can see one thing. So at the end, instead of go to a statement, we have replaced it by saying go to B3. What does go to B3 means? Go to the beginning of the basic block B3. And you can see in B4, we say go to B2. That means go to beginning of the basic block B2. And you can notice here, so there are some basic blocks which have only one successor basic block, like B1 has only one successor basic block, B2 has only one successor basic block, but B3 has two successor basic blocks. One is B4 and other is itself B3. Similarly, B4 has two successor basic blocks. One is B5, the other is B2. And if you look at B6, B6 has one successor basic block, that is itself. There are two successor basic blocks. One is exit and other is itself. Okay. So one more thing, there are some basic blocks with only one entry, like B1 has only one entry and B4 has one entry, but basic block B2, it has two entries. This is one entry point and this is another entry point. Similarly, B3 has two entry points. This is one and this is two. In fact, the speciality of B3 is it has two entry points. So if you look at B3, there are two ways in which you can enter the basic block B3, and there are two ways you can exit from the basic block B3. So there are four control paths. So this is one way of entering, this is one way of entering, and this is one way of leaving, and this is another way of leaving. So you have, this is the most general case that a basic block can have multiple, you can enter the basic block from two different program points, and similarly you can exit a basic block and go to two different program points. This is the most generic case. But you can of course have these cases also. So these, what are the other cases possible? So you have like this, or you can have, so these are all possible cases. And if you look at basic block B1, it is the simplest case with one entry and one exit. So all these things are possible. And then we always have one entry node and one exit node. And we kind of, usually if you see, if you call a function, we enter the function from the beginning. So having one entry point is usually the case in most programming languages. But you can write a program with multiple return points. But what we can do is we can add a dummy exit node. So let's say if you have this is your control flow graph. This is your control flow graph. There are multiple exit points because there is a return statement here, there is a return statement here. So instead of, when we have multiple exit points, kind of, it's not really a big deal, but if you can kind of convert that control flow graph and say that, from this, instead of this exit goes to this, and this exit also goes to this, and this is the real exit. So that way we can think that your control flow graph has one entry and one exit point. It makes our specifying our analysis, many data flow analysis algorithms easier. So one entry, one exit without loss of generality. So without loss of generality, assume single entry and exit. All right. One more thing I would like to bring to your attention. If you see here, this plain control flow, this sequence of three address tuples, the structure of loops in your program is not apparent. But if you go here and see, if you look at the control flow graph representation of your program, you can see that the basic block B3, it corresponds to the inner for loop, and the basic blocks B2, B3, B4, they corresponds to the outer for loop, and the basic block B6 corresponds to the second for loop. So by looking at the control flow graph, you will be able to identify the loops that are there in the original program. So we have already seen how we construct, how we identify the basic blocks, and how we partition this whole sequence of three address tuples into sequence of basic blocks, and we can construct the control flow graph. But if you are looking for a algorithm, more formal algorithm, it is there. So I will not go through it, but the primary intuition is this. The primary intuition is you start from you start with the first instruction. you try to keep expanding it until it's not possible, and then you start with the next instruction and you can repeat the same process. So in order to, let's try it out on this example also. If you look at this example, so you start with, let's say, instruction 1. So can we include instruction 2 in it? Can we expand in the basic block? And the answer is yes, because there is no go to statement to the instruction 2. So we can include instruction 2 in the first basic block. Can we include instruction 3? It's not possible because there is a go to 3. So we have to say that we have to stop. We will not be able to expand the first basic block beyond instruction 2. So the first basic block is 1, 2. And then you start with instruction 3. You can include 4, 5, 6, 7, 8, 9, 10, 11, 12. So not an issue. So at 12, we have to stop anyways. So this instruction sequence, it can be partitioned into 2 basic blocks. And what is associated control flow graph? This is associated control flow graph. So we have a special entry node, we have a special exit node, and this is basic block B1, this is basic block B2. So the go-to statement at the end of the basic block B2, it is replaced with this, the instruction number is replaced with the basic block number. So go to B2 means go to the instruction, first instruction of the basic block B2. So this is how we construct a control flow graph associated with a given program. And this is the most important data structure that is necessary for program analysis and transformation. So we will continue with this example. So here you are seeing a sequence of instructions, 30 instructions, and these 30 instructions, they are associated with the quicksort routine. And this is the associated control flow graph. What we will do now is, we will, if you go through this sequence of instructions, and if you do the construction, you can verify that the resulting control flow graph looks like this. So what we will do right now is, we will see what kind of optimizations we can apply on this control flow graph. So I will switch to a different set of slides now. Can you see the changed slides? Are you able to see the changed slides or? Okay. So we have seen, in the last class, we have seen how machine independent code optimizations work but when we were looking at these machine independent code optimizations, we are looking at program representation at a certain level. And today we will see how these machine independent code optimizations work on a program representation, on an intermediate representation, which is of a lower level. And I would like you to keep this idea in mind, that the same optimization algorithm that you would like to apply, the specific algorithm, the specific details could vary depending upon the program representation that you may have. So if you want to do certain machine independent optimization on an abstract syntax tree representation, you may have to take certain approach. But if you want to do the same machine independent optimization on a control flow graph representation of the program, you may have to take a different approach. So please keep that in mind. The optimization that we would like to perform, the algorithm for it, the approach for it depends upon the specific IR on which we are working on which the compiler is working on. So here is the code for the quicksort algorithm. So we will not go through the code, just yeah, so whatever it is, it is. But what we are doing here is we are looking at the control flow graph representation, not of the whole quicksort function, but we are looking at the control flow graph representation of this chunk of code, starting from here to here, and how we can perform, how we can optimize this chunk of code is what we will be looking at in the next few minutes. One more thing that I would like to bring to your attention here is this control flow graph representation. It is on a per function basis. You know, your C program is a collection of functions. So every function has an associated control flow graph. And how how the control flow graph for different functions interact with each other, that is a different kind of problem. So right now, what our focus is on, you take a function in a C program and you construct a control flow graph representation of that function. And we want to see how we can improve the quality of code by applying different optimizations on the control flow graph representation. So if you see, here is the code. So on the top left-hand side, you can see the code. This is the code corresponding to the quicksort function. And so on here, you can see this is the control flow graph representation of that code. You can see there are 6 basic blocks. And the basic block B2 here, this corresponds to this loop. And the basic block B3 here, let me write as, so this one is B2, this gets mapped to B2, this gets mapped to B3. And then you can see there is an if statement here. This if statement is there in basic block B4. If this condition is false, you break from the loop and go to basic block B6. So here, the statements here, they correspond to, they will be present in basic block B6. And if this condition is, this is the true, you come out, this is the true path. And if this is false, if this condition is false, then you fall through. And the statements here, they are present in basic block B5. And at the end of the basic block B5, you go back to the beginning of the while loop. That is, you go back to the beginning of the basic block B2. This is how, and then the statements that are present here, so they are present in basic block B1. So this is how your source C program is mapped to different basic blocks in your control flow graph. So now we will see a sequence of optimizations. I want you to pay attention. After some point, you just it gets overwhelming and you kind of lose track of what exactly is happening. Not because it is something deep is happening, but because there is a lot of detail involved. But please try to tag along with me and see what is happening to the extent possible. So the first optimizations that we can do on this control flow graph is what are called as local optimizations. What is a local optimization? In a local optimization, you work within a basic block. So if you look at basic block B5, within basic block B5 and B6, we are applying an optimization called as common subexpression elimination. So how is this happening? If you see this 4 star I and 4 star I, this is getting computed twice. So this is a redundant computation. And similarly, let me use a different color. You can see 4 star J here and 4 star J, it is being computed twice. So what we can do is we can replace this, the same thing is happening here. Uh, this is 4 star I and this 4 star I is getting computed twice. These are the same. These are the same. And then instead of using two different colors, I just connect them so that it's easy. This 4 star N and this 4 star N, it is being computed twice. And the reason why you are getting this redundant computation is if you look at basic block B5, you are accessing the array element A of I two times. And you are accessing the one is a read and one is a write. And you are accessing the array element A of J twice. Again, one is a read and other is a write. But each of these array accesses, they induce a computation once they get lowered to the next level of IR. The same is the case in basic block B6 also. So what we do is by applying an optimization called as common subexpression elimination, specifically local common subexpression elimination, because we are trying to identify redundant computations within a basic block. So we figure these optimizations, we identify these redundant computations and we eliminate them. So how do we eliminate them? We replace this 4 star I with the T6 because the value is already present in the variable T6. So you propagate this value to here, you propagate this T8 value to here. This is what we are doing. And so this is one optimization. So after this, after local common subexpression elimination, what you can see is this here we are using this T7, just pay attention here. We are doing a write to variable T7 and we are using it here. But you can see that we don't need to do this copy of T6 to T7. Instead, we might as well use T6 directly here. We might as well use T6 directly here. This optimization is called as a copy propagation optimization. Similarly, so T8 is equal to T10. You can directly use T8 here. I think someone is talking. So like that, you can look at how this works in basic block B6, but I hope you get this idea just by looking at this one particular example that we are assigning T7 is equal to T6 and we are using A of T7 in this particular statement. But instead of using T7, we might as well just use T6 there. And the same argument applies for other transformations that we are doing. So we do copy propagation optimization. After we do the copy propagation optimization, the variable T7 and T10, T12, T15, they are no longer live. They don't have any, we are not using them because after the definition, so the corresponding assignment statements become dead. We apply a dead code elimination optimization and we remove those statements. Great. So this is how the whole control flow graph, how the transformed basic blocks B5 and B6 look after these optimizations: local common subexpression elimination, copy propagation, dead code elimination. I want to bring to your attention one idea that if we start with the order in which we apply these optimizations is important, because if we do copy propagation first and then local common subexpression elimination, then what happens is copy propagation optimization wouldn't be effective. And similarly, dead code elimination wouldn't be effective. So this particular order in which we apply these optimizations is important in order for them to be effective. So now we go to what are called as global optimizations. What are global optimizations? Global optimizations means we do optimizations across basic blocks. Yeah. So global, this is what I was saying. So global means optimizations are done across basic blocks. So now if you see, look at the statements which have the same color. So here you can see T2 is in olive green color, and so this one and this one we are computing 4 I. So it's a redundant computation, but this redundancy will be uncovered only if we analyze the control flow graph across basic blocks. Similarly, this is this one and this computation and the 4 J computation, it is a redundant computation. And then we have here this here and here, this is again a redundant computation. So actually this computation here, this 4 I, it is this is available. Either you take this particular path or this particular path, you can reuse the value that is computed and stored in variable T2. So what do we do? So we take this basic block V5 and replace this 4 I with T2 and 4 J with T4. Same thing here. So we replace T4 I with T2 and T13 is equal to T1. Yeah, so T13 is equal to T1 because 4 N is available. The value that is associated with 4 N is present in variable T1. So here in global common subexpression elimination approach, in this optimization, we try to uncover redundant computations in our program by looking at the program by looking for optimization opportunities across basic blocks. And this is the transformed code we have. So now after doing GCSE, we have to do copy propagation again. So we have to do copy propagation, we have to do dead code elimination again. So let's see how it works. So if you see here, you can see that T6 is equal to T2. Where is it? Yeah. So you can see here, just want to highlight here, this T6 is equal to T is equal to T2 and X is equal to A of T6. Instead, we can directly propagate the value that is present in T2 to A of T6, which makes this statement dead code. So we have to do copy propagation and dead code elimination again. And after that, we get this control flow graph. And once we get this control flow graph, now new redundancies are exposed. So for example, here you have, let's focus on this A of T2. So we are, A of T2 is an expression which has a value. And this value is, the same value is being used here in this statement. Similarly, A of T4 is an expression and its value is associated, the same value is being used here. This particular optimization, this particular opportunity for optimization is not exposed before, So why is that? Because here we are accessing A of I, and so here we are accessing A of I, and here also we are accessing A of I. But what happens is when this A of I gets mapped to a lower level IR, the lower level IR associated with this A of I and with this A of I, they are looking different because we are using different temporary variables. But after doing GCSE and after doing copy propagation and dead code elimination, what happens is we will learn, the compiler learns that the same array access is being made in both these places, So the value that is being read here, you might as well use it here as also. So new optimization opportunities gets exposed. So we have to use GCSE again. So this is one important idea, that just because you have applied an optimization once doesn't mean that you are done with it. You may have to apply that optimization again, because after some program transformations, new optimization opportunities would have been uncovered. So we apply GCSE again. So how do we apply GCSE? So whatever the value that we are storing in T3, we kind of say X is equal to T3. And so there is one important question. Similarly, here we say, T5 is equal to T9 is equal to T5. And if you go here, that's what we do. So we replace X is equal to T3, because A of T2 is present in T3. We say T9 is equal to T5 because A of T4 is present in T5. And then here X is equal to A of, again X is equal to A of T2. So we say X is equal to T3. This is optimization that we do. But what we are not doing is T14 is equal to A of T1. We are not replacing T14 with is equal to V. Okay, so here, so there is a question which I would like you to think: why are we not transforming this statement into something like T14 is equal to V, because A of T1 is equal to V, right? So we might as well use the value of V here in this statement. Why are we not using it? So why this transformation is not a valid transformation? So there is a very important subtle reason that I hope you are able to see. That is, what happens is you are saying V is equal to A of T1 here, and the program before reaching this particular program point, the program can go along this loop. When it goes along this loop, it's no problem. Again, it comes here, it goes along this loop, no problem. Again, it comes along this path. But when it comes along this path, there is an issue, because there is an assignment to the array elements. A of T2 is equal to 9, A of T4 is equal to X. When this assignment happens to this, these two statements are problematic statements. We have to be very careful, because when these array elements are updated, there is no guarantee that a assignment to A of T2 wouldn't go and affect the memory location that is associated with A of T1. So there is no guarantee. How do we prove that T2, let me use so in order for us to be able to use it here, we should be able to prove that T2 is not equal to T1 and T4 is also not equal to T1. Because if T2 is equal to T1 or T4 is equal to T1, and if we read that value V here, then the value that we associate with that particular memory location, it's a stale value. It's a stale value, and we don't want to do it. It is not a safe transformation. It is not a safe transformation unless we prove, unless we can prove this, that unless we can prove that T2 can never be equal to T1 and T4 can never be equal to T1. Unless we prove these two things, the transformation that T14 is equal to V, it is not a safe transformation. So this is a very important idea that I want you to understand completely, because later on when we study data flow analysis, this particular idea kind of forms the basis for many ideas that we see there. So in order to perform certain transformation, we have to prove that, that it is a safe transformation. So in this particular case, it's usually very hard to prove this, something like this. So what we do is, like we say, we just leave out on that optimization opportunity. It could be true, but we don't know for sure. We just leave it as it is, because we want to preserve the program semantics. And then again, we do copy propagation, we do dead code elimination, and finally the transformed code looks like this. So we started with some control flow graph. Finally, you can see the size of the basic blocks B5 and B6, they have shrunk substantially and there are very few instructions. So this whole thing is fantastic. We did eliminate redundant computations, and we did eliminate dead code, and we substantially improved the quality of code. But then, so in compilers, how different optimizations interact with each other and how they will impact the execution time of the final program, it is very hard to predict. Because what happens is in this whole program transformation, one thing you can notice is the variable T1, it is being defined here and it is being used here. And it is not used along this path at all. If you see in this basic block, it's not used. In this basic block, it is not used. And in the basic block B5 also, it's not used. And similarly, if you look at variable T2, variable T2 is defined in basic block B2. It is not used in B3, but it is used in B5. So usually what happens is these, all the variables that are there in our programs, we want to promote them to registers because memory accesses are expensive. So in the process of, we are very aggressive in our optimization approach in terms of eliminating redundant computations. So what we did is, so whatever the value of 4 star n, we are computing, we are storing it in T1 and we are reusing it here. It's great, but then we are increasing the register pressure on the registers because the lifetime of this variable T1, earlier it is locally confined to this basic block, but now it is defined here and it is used here. So if you promote variable T1 to a register, it will just hog that register and until the control flow enters B6. That is a very expensive thing to do because we are not using T1 at all. We are not using T1 at all in this path. And if we allocate a T1 a register, it simply hogs a very, very valuable resource and it can induce many memory accesses if a sufficient number of registers are not available. The same thing with T2. So earlier, it is used locally within that basic block, but now we have increased its lifetime and it is going from here to here. So again, it also puts pressure on the registers. So on one side, in the process of optimizing our program by eliminating redundant computations, we increased inadvertently, we increased the pressure on registers. And it can have a negative, it can potentially have a negative impact on the performance of the program. Because if you are not able to do a good job with the register allocation, then the number of main memory accesses will increase. And main memory accesses are much more expensive than multiplication operation in modern computing systems. By and large, we have to take it with a pinch of salt because depending upon the working set size, uh, the memory accesses might be served from cache, in which case it may not be that expensive. It depends on many other factors, but what I want you to appreciate here is on one side, we want to eliminate redundant computations. On the other side, because of that, we are increasing pressure on registers, and how these two things interact with each other and have an impact on the performance of the program, it is not easy to predict. We can only use some heuristics and do it, but there is no sure shot way of doing it. And also you can see here, we have applied multiple optimizations and it's important that we apply optimizations in a certain order. And we may have to apply some optimizations multiple times. And some optimizations will have good effect on some programs and some optimizations can have a negative effect on some programs. So this idea of given a program, for a given program, there are two questions to answer. What optimizations to enable? What compiler optimizations to enable is one question. Second question is, in what order we should apply? In what order the enabled optimizations, OPTs, should be applied. So these are the two questions. This is a very difficult problem to answer, and this is what is called as a compiler phase optimization problem. This we call it as compiler phase interaction problem. So there are many research works on it. In one class, I will kind of give some strategies that are being used to solve this. In a later class, I will do it, but not in the next couple of classes. We will revisit this problem, and I will provide you some nice couple of interesting approaches. So some of you who are doing research in the space of compilers, we can, this problem could be of interest to you. With this, I will conclude today's lecture. And if you have any questions, you can ask me now. I think that's all.